Our next speaker is Basir Kazimi from Forschungszentrum Jülich, speaking about making the clip model segmentation-aware. Basir leads the Deep Learning for Electron Microscopy group, and his research focuses on integrating deep learning with electron microscopy to enhance material characterization.
All right, thank you very much for the introduction, and welcome everyone. I'm Basir Kazimi from Forschungszentrum Jülich. Today I'll talk about how to make the clip model segmentation-aware, and we are doing this with a case study on high-resolution transmission electron microscopy images. So as most of you already know, the standard foundation models like CLIP, they are good at aligning images to descriptive captions. For example, you have a transmission electron microscopy image, and the description, like this is a TM image of gold nanoparticles, for example. And two different encoders, one for text, one for image, could map this into a latent space that is similar for both, if they are similar, of course. But when it comes to very fine-grained and structured details, which is desired for scientific imaging, for example, here, if you have an transmission electron microscopy images of multiple nanoparticles, and you know the specific material type, the number of nanoparticles, the standard clip model would struggle with it. And that's why we present the segmentation-aware clip to tackle this problem. Many of you who are aware of this clip variants would argue that, okay, there's seg clip already that does this. But as you might know, the seg clip focuses on unsupervised methods to do segmentation, and they are focusing from text to segmentation. But our focus is to go from images to textual description, because we already have the segmentation mask that we can leverage. We are working with high-resolution TM datasets. These are of different materials. We have silver, cadmium selenide, gold nanoparticles. They are of different sizes in diameter, so 5 nanometers, 10 nanometers, 2.2 nanometers. And they are all taken with different electron dosages, which is very important for the quality of the images. And they are, as you can see from the scale bar, they are all of different magnifications. So these details are very important. What we did with this is using those information that I already talked about, the material type, the diameter of each nanoparticle, electron dosage, and the segmentation masks that we already have. We used some automated tools to sentensify all those information. For example, we have a sentence saying this HRTM image shows gold nanoparticles on a UTC substrate. It contains 8 nanoparticles. We talk about sizes, aspect ratios, the roundness, and the locations of each nanoparticle with respect to the image dimensions and also the electron dosage. So this information is included in another example of the image, but this is paraphrased so that the model doesn't only understand to, okay, I should just focus on this part of the sentence. So that's why we diversified the information and paraphrased this, but including the same kind of information. In terms of model architecture, we first trained this using the vanilla clip architecture, but then we also compared this to our approach, which is the segmentation-aware clip, and this uses the segmentation masks with an extra segmentation head. So here are some details about the data set. We had around 1,200 images for training and 158 for validation and test. The images are of 512 by 512 pixels. During training, we batched them to 48 examples each. And then for the data, for the normal clip, we have only the image caption pair, but for the segmentation-aware, we have the segmentation masks as well. We trained both models for 200 epochs, the general cross-entropy laws for segmentation, and for contrastive learning. For aligning the images and text, we used cosine similarity as the metric. We optimized this using Adam, W optimization, and the evaluation metric later on to see how the images are aligned to the textual description. We used the recall as the evaluation metric. So after training, we tested it on the test data, and we show here that the segmentation-aware clip compared to the vanilla clip gives a better recall scores on both image-to-text and text-to-image. You could see this in the similarity metrics, where on the y-axis you see the image samples and the text samples are in the x-axis. What you want is this diagonal line to be as bright as possible. Believe me when I say that the one for the segmentation-aware clip is brighter, but if you don't believe me and if you cannot see it well here, I could show you some concrete numbers here, and you can see that for all recall thresholds, recall score at 1, vanilla clip is 25.95% on the image to text, and for the segmentation-aware, it improves by 10%. And as we go up to recall score at 10, the score increases for both. And the same trend is there for the text-to-image. So in conclusion, we presented an extended segmentation-aware clip applied to scientific imaging, and a case for this study was electron microscopy. And we showed that this leads to a better recall compared to vanilla clip. But why do this anyway? Why align the images to textual description? Because later on we want to go from the original input TEM image to textual description to understand specific details about the image, or we want to generate synthetic data from textual images. So we give some textual description and train a model to give us electron microscopy image. We could also extend this to multimodal training, so not only transmission electron microscopy image and the textual description, but also other details or other modalities of electron microscopy. We could also extend it to other downstream tasks, image generation, segmentation, textual description, or any other idea or insights that we want to extract from this trained model. Yeah, I'm heading the deep learning for electron microscopy group at Forschungszentrum Jülich. We are a small group of 4 researchers, and this is a joint lab between IS9 and Enskroska Center, both institutes at Forschungszentrum Jülich. We also have some collaborations with the in situ microscopy group at KIT. And if you are at the intersection of deep learning and electron microscopy and have some cool examples that we could collaborate on, please get in touch. Thank you very much for your attention.
Thank you for the presentation. Oh, there's people rushing for the microphone. No? Yes? Okay. Thanks.
Thank you for your talk. It's quite interesting to me, the topic. So I have a question with detailed architecture of the network. So you have like a word embedding from the clip and also the image embedding. You want to reconstruct the mask. So you contacting it simply with the 2 embeddings or use different techniques for the embeddings. If so, if you just use the image embedding to reconstruct the mask, it's better, or do you have any study for that? Yes, that's my question.
Yeah, so in this study, what we did was similar to what CLIP does. So the image encoder and the text encoder, they both produce a vector, and you try to pull them together pull them together as much as possible so that they are very similar. And here we only use the output of the image encoder to do segmentation, but that would be an interesting idea to do it with the text encoder's output as well.
Do similar thing with clip?
So that one, the first difference is, of course, that it is trained on natural images, right? And it's trained on lots of images. For us, it's only around 1,200 images. So it's very domain specific. What I would say that if we try to fine-tune the segment anything model and compare this, that would also be interesting to see. Yeah.
Okay, so there is no like structural differences. It's mostly the training.
In terms of how you, in terms of the architecture, in terms of the
architecture.
There's differences, of course. So for example, here for the encoder, we used ResNet, but one could replace this with the VIT architecture, so vision transformers. And for the clip, the text encoder is the BERT model. I'm not quite sure what the text encoder for the segment anything model is. So yeah, there might be some differences in that as well.
And we have time for one more question.
Perfect. Yes, thank you very much for your presentation, first of all. I got quite surprised about the number, the prompt that you used into your model was quite big. I just wanted to ask you how many samples of that did you use, and if the prompt has to be that big for the model to work actually, or why did you use such a prompt?
So yeah, the first example that I showed was for a TEM image with 8 nanoparticles, so the prompt was quite big, but not all of them had that many nanoparticles. So the second example was, for example, quite short. And what we did during training was we set a maximum number of tokens to use. So this example that I showed, the very long one might not have been used during training. Yeah.
And related to the question of how many prompts did you actually use in your data set? How many did you get at the end of the day for the training?
How many prompts for the same image?
I mean, no, for the data set you trained with.
So we had around 1,200 images and caption pairs during training, and every time we, so for every image, the prompts are different, even though they contain the same kind of information. So one prompt for each image.
Okay.
But for separate images, the prompts, even though they contain the same structure or the same kind of information, the structure is different because it's paraphrased and the locations are switched.
That makes sense.
Yeah, so that the model doesn't memorize the locations.
Exactly. Yeah. Thank you very much.
Thank you.
Yes, let's thank our speaker again.
Thank you.